Thank you guys all for coming. My name's Jake, and I'm joined here by Trevor. We both work at Stripe on the Sorbet team, and we're going to be talking about compiling Ruby to native code with Sorbet and LLVM. So a couple definitions here. Sorbet, if you're unfamiliar, is a type checker for Ruby. It's something we're really excited about. You might have seen Matt's mention it very early on in the keynote, that static typing in Ruby is very much happening right now. If you've ever been curious about should I use static types in my Ruby code, my advice to you would be absolutely, and I would encourage you to try Sorbet out. It's a lot easier to get started with than you might think, and it, in our experience, and I guess the experience of a bunch of other companies that have started using it, has a lot of compounding benefits over time. So the other kind of definition that we want to get out of the way in the beginning is LLVM. So LLVM is a kind of like framework or toolkit for building compilers. It takes all of the hard part of building a compiler and puts it behind a nice little interface, and all we have to focus on is how to take our source language that we want to compile, in our case Ruby, and convert it into native code using LLVM. So when we smash those two things together, we get the Sorbet compiler, and you can, I have to apologize here because I'm a compiler writer, not a graphic designer. I tried to put some wings on our Sorbet logo to make a dragon, and it came out looking like a Sorbat. So anyway, we do have stickers of this logo, and you can come grab some from us after the talk. So our agenda is going to look a little bit like this. We're going to first talk about the motivation for the whole project, starting from like Stripe's motivation, like why Stripe cares about performance at like a base level, and then transition a little bit to talk about why we think that to improve performance at Stripe that we want to build a compiler for Ruby. Then we will, I'll hand it off to Trevor, and Trevor will tell you all about how the compiler works and how we've implemented it and all the cool stuff that it can do. And then we'll come back and talk a little bit about how we're actually adopting it in production. So let's dive into that first one, why Stripe cares about performance. So for those who are unfamiliar, Stripe is like a software company that basically provides an API that lets you pretty much build a business. Imagine any particular part of your business that you might need to do that involves money, like accepting payments or coordinating payouts or managing taxes or giving loans, receiving loans, doing invoices, subscriptions, all sorts of different things that involve moving money around in your company. Stripe has an API for it. So it has all these different features, and it does a lot of different stuff. And one of the features that we actually consider in the API is how fast it is. Because if two developers are thinking about, okay, which API should I use for building my business, and they're feature compatible except that one API is faster than the other, chances are they're going to choose the faster one. So we want to make sure that our API is as fast as possible for our customers. So that's a little bit about why Stripe cares about performance, but that doesn't really answer the question of why we think we need to build a compiler for Ruby to address that performance. So some more background is Stripe uses Ruby extensively. It powers our most important services, including the Stripe API. Hundreds of engineers are writing Ruby at Stripe daily, amounting to editing millions of lines of code that's kind of organized in a monorepo. And one keynote here is that Stripe's Ruby is, again, very, very heavily typed. We wrote Sorbet and have been adopting it over the past 3 years. And at this point, Stripe's codebase is probably the most typed Ruby codebase in the world. So we really wanted to tap into this type coverage, and we'll see about, how the compiler leverages those type annotations a little bit later in the talk. So when we kind of zoom in on where the API spends its time, we see that it kind of breaks down into two components. There's the I/O component, where it's time spent waiting for the database to come back, or time spent waiting for some partner API to come back, like waiting for a bank to respond to you, or something like that. But then there's a substantial portion of the request that is just blocked on Ruby code. So contrary to like what people will tell you with like simple CRUD apps is, it's not all for Stripe at least blocked on I/O. We do actually want to make the Ruby code faster in order to speed up the API. So when we zoom in on the Ruby component of this, what we see is it's actually like really fragmented. There's dozens of teams that are maintaining all sorts of different code that lives in any given API endpoint. And instead of it just being this one big block that we could try and speed up, it's broken into these like small things that are kind of hard to speed up individually. And at Stripe, this amounts to like dozens of teams worth of code. So when we one way to make this Ruby portion of the API request faster would be to figure out what's the slowest request. So maybe it's like this blue block of code that's sitting there in the middle. We could figure out which team owns that slice of code, ask them to make it faster, and maybe we do that, and they do it like really well, and they speed it up like by 2x, so that it's like much, much faster than it used to be. Even if we did that, it would still have a tiny little divot on the end-to-end API request because there's so much other stuff going on in an API request. So if we were to take this approach and actually have a real impact for the end-to-end latency, we would have to go ask pretty much every team at Stripe, stop what you're working on, go make your API endpoints faster, take the code that you own, and like stop working on the features and bugs that you would have otherwise been prioritizing. And like, imagine how annoying that would be if that was what happened at your company, where like someone said, nope, your whole roadmap is gone. You're going to focus on nothing but performance for like the next 6 months. Like, you'd probably be really annoyed. So what we were really looking for was some magic wand that we could kind of wave and make all the Ruby code faster all at once. And the goal here is that then by speeding up all the pieces, everyone else at the company can focus on doing what they do best, namely like building a really good payments API. So that's kind of the justification for why we want to speed up Ruby. And we have a couple of approaches here that we could have done. The most common question that we get is like, why not just use an alternative Ruby implementation that's potentially faster, like Truffle Ruby or JRuby or something like this. And we did consider this. We spent a little bit of time thinking about it, and ultimately came to the conclusion that given the size of the Stripe API and how complex and important it is that it remains always available, it was going to be hard to do some sort of incremental migration. That the Stripe API, in order to get it to run Truffle Ruby, we would have to run all of it on Truffle Ruby or all of it on JRuby all at once. And we were really looking, again, for something that we could show incremental progress over time. And then the other downside here is you kind of have to abandon the Ruby ecosystem, that like you're adopting some JVM ecosystem or some alternative Ruby implementations ecosystem. And at Stripe we've built up just tons of collective knowledge about how to operate Ruby and like how to use Ruby and all these different tools like that work in production. And we didn't want to have to give up any of those. We wanted to continue to work with the existing Ruby VM that we had a lot of domain knowledge about. So at that point we were like, okay, well maybe we should consider building our own implementation, and one big question there was, should we build a JIT compiler like Truffle Ruby and JRuby or YJIT that was just merged into Ruby 3.1, or should we build our own ahead-of-time compiler instead of doing this JIT compiler? So the key advantages of an ahead-of-time compiler, which is what the Sorbet compiler is, are the first one is we can actually take the Sorbet's view of the type statically and use that to inform how to compile the code. So if Sorbet knows that this thing is always a certain type, it can take fast paths that operate on that type and not have to kind of wait for the production information to come in and make a decision on how to optimize it based on that. And then the other thing is, conceptually, ahead-of-time compilers are just a lot simpler. The output of an ahead-of-time compiler is a pure function of the code that you give it, whereas a JIT compiler, the output that the generated code will be a function of not only the Ruby code, but also like the requests that come in and the timing in between when they come in and what data they come in with and all these different sorts of things. And so if there's bugs or there's like weird performance characteristics in JITted code, it makes it a little bit trickier to track down. And so we were really attracted by the relative simplicity of an ahead-of-time compiler. But importantly, we can actually still do both. There's nothing preventing us from using the compiler for the parts that the compiler will work well on, and using the JIT for all of the other parts. And Trevor's going to talk a little bit about how the implementation that we've chosen for the compiler reuses the existing Ruby VM and works like alongside it. And again, that was part of our goal with having an incremental migration. So with that, I would love to hand it off to Trevor, and he will talk about how the compiler actually works.
Thanks, Jake. So yeah, as Jake mentioned earlier, the Sorbet compiler is made up of kind of two main components, which are the Sorbet type checker and then a code generator that's developed using LLVM. So just to get a sense for what Sorbet looks like when you add it to a Ruby program, let's run through a really quick example. So we have this function here. It takes a single argument x. It's going to call map on that x, and it's going to pass a block that will just increment whatever it's given. Right? So the way that we would add Sorbet to this is to add a signature. And so what this will now say is x actually must always be an array of integers, and f must always return an array of integers. So if you look over on the right, you can see we've run Sorbet, and now it says that there are no errors, which is great. So what if we introduce one? Instead of returning the value that we had produced by calling map on x, what if we instead chain 2s on the end? Well, now Sorbet complains and says, oh, actually, it looks like you're returning a string here when you meant to return an array. So there's an error here. And so this is the kind of type information that we're looking to take advantage of, knowing that something is always an array when we're compiling the code. So the next part of the Sorbet compiler is the code generator, which utilizes LLVM. So LLVM comes with its own language kind of built in, which is basically a target independent assembly language. And this is what we target. So we take type checked programs from Sorbet and we produce programs in the LLVM IR. So you might think that adding a backend to a project like Sorbet would be an enormous amount of work. But in reality, it's only taken us about 10,000 lines of additional C++ to the code base to get to the point where we're generating shared objects. We have an additional 5,000 lines of C that go into kind of runtime support for those. So just a little bit more information about LLVM. As Jake mentioned, it's kind of a compiler backend toolkit. So it has, in addition to this target independent assembly language, it has lots and lots of optimizations built up that it can apply to those. And so, by targeting LLVM, we're getting all of those optimizations sort of for free, which is really great. And LLVM is used by many other industrial strength compilers, including Clang for compiling C and C++, GHC for compiling Haskell, and Apple's Swift compiler. So the final part of this pipeline is the native code that comes out of the code generator. So we emit shared objects, which use the RubyVM's C API for interacting with other Ruby code. So just to give you a kind of quick introduction to what C extensions look like, in case you're not familiar, we have this program on the left, which lives in mylib.rb. It defines one function foo, which takes a val and is just going to print it out. So on the right here, we have an equivalent C extension. So the init mylib function will serve the same purpose as the top level of the mylib.rb script. So that's where the method will be defined. And you can see on the first line of init mylib, we're defining the method with rb define method. We're calling it foo. We're saying its implementation is myfoo, and we're saying it accepts one argument. The myfoo function indeed takes one argument in addition to self, and is just going to use rbfun call to dispatch to the puts function inside of the VM. So this is the basic API that our compiler is targeting when it's generating code. So let's go back to the example that I showed when I was introducing Sorbet. So this is the function f that's going to call map on an array. And let's show kind of iteratively what's going to happen when we compile this program. So this part is going to be a little bit hand-wavy, and then I'm going to transform the program in ways that are kind of a little bit nonsensical, and that they will call C functions in the middle. But the point here is just to kind of illustrate what's going to happen when optimizations are taking place on the LLVM. I don't want to imply that the Sorbet compiler is a source-to-source transformation, I guess, is what I'm getting at here. So the very first thing that you need to do to compile Ruby with Sorbet is to add a compiled sigil at the top. And so this is really kind of stressing the kind of incremental approach that we're taking here. We want to be able to opt individual files into compilation and not just say you have to go all or nothing on the entire code base. So the next change is that the compiler will unconditionally check type signatures. And we can kind of show that here by moving those type signatures into the method body and turning them into exceptions when the type test would fail. So the reason for this is that the Sorbet compiler will make a lot of use of that type information. As Jake was stressing earlier, we wanted to figure out a way to leverage the type information that we have to generate better code. So as a result, we're going to check those type annotations at runtime unconditionally so that we kind of create assumptions that the optimizer can then reuse later on. So here you can see we're going to raise an exception if x is not an array, and we're also going to name the result of x.map and raise an exception if that's not also an array. So the next thing that we can do is start trying to avoid VM dispatch, which is actually quite expensive. So in this case, we know that x is an array, and we know that the implementation that it would ultimately call would be RBArray collect in the array.c library that's linked into the VM. So here's where the kind of hand waviness starts, right? I'm calling a C function here. I'm passing a block. Normally the block we would have to extract to a different function, and you would have to do a lot of setup to actually get that block into the right context where it would be used by RBArray collect. But the idea here is that we just really want to avoid that dispatch going through the VM. So the next thing that we can do is if we know what function we're going to call, why don't we actually just inline its implementation at the call site? So map, if you remember, is just going to iterate over all of the elements of the array and call the block on each element, putting that result into a new array. So you can see we've done the exact same thing here. We have our T array initialized as an empty array. We've got an index for indexing through x, and then we just iterate over x. And again, this is kind of more hand waviness but we're going to call the block on x at I, and then put that result into t. So it's kind of, very similar in spirit to the previous implementation, but now defined here instead of in the VM itself. So we can just keep inlining things at this point. Like, why not inline that block call directly into the loop body? And so now at this point, we're no longer calling that block. We're just using x at I and adding 1 directly. And we can just kind of continue applying this pattern. So where we're defining len, we could instead call directly into the length function for arrays. Where we're appending into t, we could just call directly the function where we would append into an array because we know that t is an array. And where we're indexing I, we could pick a more specific implementation that would be faster. Finally, there's this, this type check at the end where we're making sure that we're returning an array. But if you notice, there's not really anything that would change the fact that t is an array. It's initialized as an empty array. The only operations that are used with it will not reassign to it so that we know that it's going to remain an array for the duration of the program. So we can actually just remove this final type check and end up with something that looks like this instead. So the cool thing here is that we have done less type checking. We've avoided VM dispatch. We've inlined a function so that we're now doing a loop instead of calling into the VM. And just to give you a sense for what this might look like if you were to write it in C, here's a really squished up version of basically the same function. So you can see that we're initializing t with rbarray new2. We're looping over the contents of x. We're adding 1 to each element of that and then pushing it into t and then finally returning the result. So what the compiler ends up doing is sort of essentially turning Ruby into a really nice DSL for writing Ruby native extensions instead. So now I'm going to pass you back over to Jake, who is going to tell you a little bit more about how we're adopting this at Stripe.
Awesome, thank you, Trevor. Yeah, I hope you guys are as excited as I am about that. I think it's super cool that we can basically write a tool that lets you continue writing the exact same Ruby that you normally would have. All you had to do was write x.map, and you basically get this optimized C for loop that is super fast. So that's kind of the idea of how the Sorbet compiler works at a very, very microscopic level. Now we're going to zoom back a little bit and say, does it actually work in production? How can we actually take steps to make sure that it's doing the right thing on actual real production Ruby code base? So we have 3 main goals with our rollout strategy. The first one is absolutely we have to have a plan for when things go wrong, because things are going to go wrong, and Stripe is depended on by tons and tons of businesses every day. So we need to make sure that we're not breaking their businesses. Then the next one is we want to actually compare performance on real traffic. It's not enough for us to know that the compiler speeds up some arbitrary benchmark like x.map. We want to make sure that it's actually speeding up Ruby as it's written in the real world. And the last one is, again, we want to be incremental in everything that we're doing. We want to know what's the best bang for our buck at any given point of our migration. So our plan for when things go wrong is built up of multiple lines of defense. So first line of defense is pretty obvious. Whenever we make a change to the compiler, we write a test case for it. As par for the course, everybody should be writing test cases, but this catches a lot of our bugs. We've, over time, built up a really good set of test cases where every new compiler feature that we write is getting it, even more sure that we're building the right thing. But let's say that we didn't actually write a test case for something. The next thing that'll potentially catch a bug in the compiler is we take all of Stripe's Ruby tests that Stripe has written over 10 years of being a company, and we run all of them under the compiler. And if any of them fail, that'll be one more thing that potentially makes us say, wait a second, there's a bug in the compiler, and rethink what we're doing. If there doesn't happen to be a Stripe test for something, the next line of defense we have is Stripe has a pre-production or staging environment where it emulates a production environment as much as possible, but doesn't actually receive live API traffic. And so that might be one more place where we could detect a bug in the compiler and abort early if we find it. It continues from there to Stripe has blue-green deploys, so that the way that works is you deploy all of the new code to a set of servers that we call the green servers, and then you incrementally migrate traffic over to those. And if at any point in time during this traffic migration, you notice a bug, you just immediately flip back all the traffic to pointing at the previously deployed blue servers. So this helps us guarantee that if there was a change that we could detect at deploy time, it has very, very minimal impact on real Stripe customers. And then the last one is if somehow a bug managed to slip through all of these lines of defense and we had to figure it out manually, like maybe somebody complained, maybe we detected it somehow, all of the compiled code at Stripe is running in a separate host set that can be killed with a flip of a switch. So if we ever need to, we can turn something off really quickly and remediate it after the fact. And what this lets us do is iterate really on this production performance data. So we don't have to write like synthetic benchmarks. We can actually just make a change, deploy it to production, and see what it actually does for API latency. We can take these hosts that are running the compiled code, track how much time they take, and we can do the same for the other hosts that are just running normal interpreted Ruby, and we can just plot the difference over time. And so when we make a change to the compiler that we expect to speed things up, if it doesn't speed things up, we get immediate feedback on, hey, wait a second, that doesn't seem like the right change to make. And so then the next question is like, how do you know what changes to make? And so for that, we've been using StackProf. So StackProf is a stack-based sampling profiler for Ruby. It works on just normal Ruby code, and because of our implementation strategy, the compiler is just emitting code that looks as much as possible like normal Ruby code. So StackProf just sees it as normal Ruby code and can profile it in the exact same ways. So in this example, what StackProf would see is it would sample this request and see that this green box that has a bar spends the most time being run. And so for our incremental rollout, we'll say, oh, well, we would get a lot of bang for our buck from figuring out which file has a bar defined in it, putting that compiled true file, sigil at the top of the file, and moving on. And so this gives us a really concrete punch list of here's the most important stuff to compile, and we just go on down the list, which also lets us know, okay, if our compiler doesn't support some feature of Ruby, we want to implement the features of Ruby that are in these most important files before maybe some other features of Ruby. And just having this like ordered list of priorities is super important for us as we've been rolling things out. So that is kind of what we've been working on. The next steps that we have are kind of twofold. The first is we haven't quite gotten to the level of adoption that we want to internally. We've definitely been adding a lot of compiled true files, but our next most immediate term step that we're going to take is just to continue compiling more things. And once we've locked in a really large fraction of a request that's running compiled code, we're going to switch gears and focus entirely on kind of profiling and optimizing the generated code. We're going to figure out what is it doing slowly, what could it be doing better, iterating on how we generate the code, iterating on how we're using LLVM, so that we can just kind of turn this crank and make the generated code even faster. So that is pretty much it. If you have any questions, we have, I guess, 7 minutes. And also, again, we have stickers. And if you like working on large problems at scale like this that involve, I don't know, really interesting, complex solutions, Stripe is hiring. Come talk with either Trevor or I at the end, and we're happy to talk about all the cool things that Stripe is working on. Thank you.
Thank you. Yes, questions?
So it's actually cool. So obviously there are portions of this work that are reliant on the type information supplied by the sorbet annotations, but I'm interested in if there are any parts that you've discovered are portable outside of a typed Ruby context.
Yeah, so that's a great question. So one thing that the compiler will do, I guess we don't have a quite perfect example here, but imagine that, Trevor was imagining that this while loop was like a C while loop, but imagine this was actually just normal Ruby code. This while loop would be implemented as just like VM bytecode instructions inside of the Ruby VM. And to evaluate a VM bytecode instruction, it's got to do a bunch of stuff. Like it's got to call maybe 7 different C functions and manipulate a bunch of different VM data structures. And all that it's trying to do is just, unconditionally branch back up 3 lines. That's all the VM is trying to do. But why should we have to wait for 7 function calls and a bunch of C pointer dereferences to do what assembly could do with a single just jump assembly instruction? So we see that a lot of the control flow actually gets much faster, regardless of whether you have type information.
Yes. You may have touched on this at the very end, but what is the performance improvements that you've seen? Is there a nice chart you can show us or something?
Yeah, we almost had a slide that was showing some performance numbers, but we decided that it was going to just be more confusing than it was worth. A lot of the benchmarks that people are familiar with Ruby are like, they don't even type check, much less have really heavy type coverage in them. So it doesn't really matter what the compiler is doing on that because you wouldn't use the compiler to speed up one of those code bases. And if we were to show some performance improvements on Stripe's code base, that gets into like some proprietary information that we don't want to. So it's one of our goals for like, once we focus on that profile and optimize step to factor out some shareable benchmarks that we can just like kind of continuously report our progress on, but we haven't had time to do that yet. What was that? It really depends on the workload, but the last time that we shared some numbers, it was either between a 22% improvement or 170% improvement in production traffic.
I got a couple questions here from Discord. Sam W. asks, how does the compiler check that an array, in this example, the array only contains integers without iterating over the entire thing?
That is a great question, and actually, it doesn't have to. You notice that all of the optimizations that it did here didn't actually care what the element type was. If the first point where it needed to know that the element that it got out of the array was an integer in order to be able to do some operation, it would have inserted another check there. In this case, we didn't have to.
Okay, next question from chat comes from Aaron Patterson. So how does the compiler know to replace, like in this example, how does it know to replace like array.each with this particular construct? Do you have to manually put that in, or do you have an automatic way to figure that out?
Yeah, so we have a mechanism where, you know, we have well-known functions for symbols that are also well-known. So good candidates for these are classes that are all defined by the VM. You know, array and hash are very heavily used, and so we can say, if you see array.each, you probably want to try replacing that with a for loop instead, rather than, you know, dispatching to a function in the VM.
But even more than that, another case, like obviously if we know that there's a C API function in the Ruby C API that we could call to implement something, we can do that. But if you define your own methods in Sorbet and mark them final, Sorbet has a way of marking methods final that means they can't be redefined, they can't be overridden, they can't be, you know, like changed at runtime. The Sorbet compiler will compile those final methods to just C function pointers the same way as any other C function inside the Ruby library, and it will do the exact same thing for your code as it will do for the standard library code. So.
I know that Stripe is not a Rails shop. Have you either tried the compiler on a Rails app, or do you know of any external users like Shopify who have tried it?
Fortunately, no. I don't think anyone's using the Sorbet compiler except for Stripe.
Okay, another question from Discord, again from Aaron Patterson. So you showed that you're inserting type checks at the beginning and the end of the functions. Does your compiler, like, or is the Sorbet compiler responsible for removing that final type check, or are you leaving that up to LLVM to do?
So we actually do leave that up to LLVM. We kind of have a symbolic implementation of all of those so that LLVM will kind of coalesce them as much as possible. And then it's able to tell when they're redundant. And so, you know, for the assignment of T initially at the beginning of that while loop, here, one of the things that we would do is also emit an assertion that says, hey, T is going to have, you know, type array because we've initialized it as an empty array, which will, you know, because T is never reassigned to, that will end up kind of allowing LLVM to remove that final type check.
Yeah, like specifically LLVM lets you encode arbitrary predicates and lets you say, please at this point assume this predicate is true, and then it will use those predicates to like inform the rest. So you can make it as arbitrarily complicated as you want. It doesn't have to just be type tests.
Oh, is there a minimum type level that you need for this to work? I'm curious if it like false or true, or if you have to shoot
Yeah. So the minimum type level that is required for this to work is typed true. So if you're not familiar, Sorbet has various strictness levels that you can put in a typed colon comment at the top of a file. They range from ignore to false to true to strict to strong. True is the first one at which it will actually like look inside of method bodies. False, it will basically only look at like syntax errors and whether your constants resolve. And the input to the compiler is the output of the typed true step. So Sorbet at some point generates a control flow graph of all of the like Ruby code essentially, and then it walks this control flow graph, assigns a type to every variable in the control flow graph, and that typed control flow graph is the input to the compiler. And we go straight from that typed control flow graph into LLVM IR.
All right. Aaron Patterson had one more question, but I think we're over time, so
Okay.
thank you so much.
Thank you.